Does a butterfly flapping its wings in Brazil really cause a tornado in Texas? To scientists, this isn't poetry, it's a legitimate mathematical question. Chaos theory studies how small differences in initial conditions can lead to radically different outcomes, even when the system follows strict deterministic rules. Today, we'll explore the math of chaos, simulate chaotic systems, and uncover how unpredictability shapes weather, nature, engineering, and life. Chaos theory isn't about randomness. It's about patterns that are so sensitive to initial conditions that they look random. It's the study of deterministic systems that can't be predicted long-term, no matter how precise the math. Chaos in mathematics and physics refers to the behavior of deterministic systems that are highly sensitive to initial conditions. This means that even though the system follows precise rules, deterministic equations, tiny differences in starting values can lead to drastically different outcomes over time. In other words, chaos is unpredictable but not random. It arises from order. The equations governing a chaotic system are perfectly logical, yet their outcomes cannot be forecasted long-term because of this sensitivity. To understand chaos, we need to revisit classical physics, Newton's universe, where everything is predictable if we know the laws in the initial state. But even simple systems, like the weather, refuse to behave so neatly. A tiny difference in the starting point can send predictions spiraling out of control. Let's start with a simple example, the logistic map. It looks innocent, but it hides chaos within a single equation. This equation models population growth, where R controls how quickly it grows. For small values of R, the population stabilizes. But as R increases, the system becomes unstable, oscillating, then chaotic. This is how chaos hides in something as simple as reproduction. Now imagine predicting the weather. You take today's temperature, wind, humidity, feed it into an equation, and expect to know tomorrow's forecast. But change just one decimal place in your starting condition, and in a week, the prediction collapses. This idea was first discovered by Edward Lorenz in the 1960s. While running weather models, he re-entered initial data rounded to 3 decimals instead of 6, and the result was completely different. The computer's rounding error revealed something profound. The universe can be deterministic and still unpredictable. The shape that emerged from Lorenz's equations became iconic, the Lorenz Attractor. A butterfly-shaped pattern that never repeats but never escapes its boundaries. It's not random, it's a strange attractor, a mathematical structure that defines the limits of chaos. The Lorenz Attractor showed us something new, deterministic chaos. Every point follows the rules exactly, yet the outcome is forever uncertain. This discovery shattered centuries of confidence in prediction. It told scientists, even perfect equations can't guarantee control. Chaos is everywhere. In biology, it appears in heartbeat rhythms and population cycles. In economics, markets swing wildly due to nonlinear feedback. In engineering, turbulence and fluid motion resist exact modeling. But chaos isn't bad, it's powerful. Weather prediction, for instance, uses chaos-inspired models that run thousands of slightly different simulations, called ensemble forecasting. This helps us estimate probabilities, not certainties. Even art and music embrace chaos. Fractals, like the Mandelbrot set, are born from chaotic equations, yet they create stunning order. In sound, chaotic modulation produces natural, organic tones. Let's do a simple thought experiment. 2 identical systems, same equations, same setup, but we change just one tiny initial value. At first, they move together. Then, slowly, they drift apart, until their paths have nothing in common. That's the butterfly effect. So, does a butterfly's flap really cause a tornado? Not directly. But it reminds us that the world is a web of interconnected systems, beautiful, complex, and unpredictable. Chaos theory doesn't destroy order, it reveals a deeper one, where even unpredictability follows its own kind of logic.